My name is Nicholas Dorico. I'm a solutions architect for Oracle, for MySQL specifically at Oracle. I'm based in the San Francisco Bay Area, and I've seen so much Kubernetes deployments and uptake in the past few years that I'm very excited to have. Now we're very close to having the MySQL operator for Kubernetes officially by the MySQL team. And it's my pleasure to present to you or to introduce to you this this new software from us. So for since the beginning of MySQL 25 years or more ago, people use MySQL on premise, of course, on compute nodes, or we used to call them computers, and virtual machines, and so on. So this remains a very valid way of using MySQL. And we've tried to make it easier, in fact, by creating something called MySQL InnoDB Cluster that handles high availability. Used to be a pretty challenging thing to do with MySQL, but MySQL InnoDB Cluster is a framework for let's say using MySQL in a high availability setup on premise. And it's pretty easy to use, pretty easy to manage. It has automated failover, but it is not exactly a managed service. It's not. It just is not. And so the past, maybe 5-10 years, and people start to use cloud a lot. There's a lot of cloud migrations. In fact, Oracle Cloud has a MySQL database service that we provide that is fully managed. It's the most likely the easiest way possible to use MySQL. Just call to an API to start the service or shut down the service and so on, or do it right from the web console. So that one is fully automated. But there's also the other way, which is to use MySQL in a containerized manner. And with containerization, the very popular way to do orchestration and management of containers, including of MySQL, is to use Kubernetes. And like I said, I've seen so many deployments now of Kubernetes and MySQL in Kubernetes. It's actually been, when we use MySQL InnoDB Cluster, it's already pretty easy to use overall within Kubernetes. However, the MySQL operator takes that to the next level in terms of how easy it is to set up, to manage. With Kubernetes and InnoDB Cluster together, we get, of course, automated failover. And while it is not a fully managed service in the sense of what you would expect as a cloud service, it is pretty close. It's a mostly managed service when we use the MySQL operator and MySQL InnoDB Cluster in Kubernetes. So what is Kubernetes? Like I said, it's kind of an orchestration framework or platform for containers. And when we use MySQL as a container, Kubernetes makes it very easy to create clusters of MySQL servers and achieve high availability. But to really make to make it better for the Kubernetes person who's handling this, we have there are basically Kubernetes operators to help to manage the the various services. And so the goal that we would have with MySQL in creating an operator is to bring the simplicity and the value of the MySQL InnoDB cluster to the Kubernetes environment, and create a situation where it's very easy to deploy MySQL InnoDB clusters, maybe with a simple one command line in Kubernetes, as well as provide self-healing capabilities and so on. So this is what we have done. But before we even get to the operator, I just want to introduce, in case somebody is a bit new to Kubernetes, some of the words we're going to be using to describe the fundamentals of Kubernetes and how MySQL is used in Kubernetes. So the most basic thing in Kubernetes is a container, okay? And the container, you can think of it as an atom. An atom is a one thing that is indivisible. So the container is kind of like that, is a program that runs in it runs isolated from other programs. It thinks almost it's like on its own computer. And so the program or the framework that let's say runs the container is called the container runtime. And Docker is a good example of such a thing. But then Kubernetes takes these containers and puts them in something else called the pod. So just as container is, let's say, an atom, then the pod is like a molecule where one or more containers are put together. And from Kubernetes perspective, it thinks of a pod as its most fundamental working unit, but it thinks as the containers within the pod. It knows that if all the containers are running in a healthy manner, then the pod is healthy. So then everything is good. And if one of the containers in the pod is not working, is failed, then Kubernetes will say, well, the pod is failed. So then it will need to try to fix that. There is one interesting thing is that we cannot make what we call sidecar containers in a pod. And these are kind of the exception to what I just said, where you could have a you could have, let's say, an application running in its own container, the main application, and then you put a sidecar alongside in the pod, and then if Kubernetes will think the pod is working okay if the sidecar is working, even though the main container is not working. So why, in what circumstance is that useful? Well, if somebody is making that's an agent or some kind of angel process to make sure the main container is working well, then that would make sense. Okay, so let's just keep that in mind, the concept of a sidecar container, because we'll see that again in a few moments. And then another concept is deployment / replica set. So the deployment is sort of like an evolved replica set, and I may use it interchangeably, one or the other. But essentially, what this is that it's a group of pods. So if you think about it, when you create, let's say, a web application, you may want to scale it as more users come into to use the service. And the way to do that in Kubernetes is you put them in the deployment, and then you can say, okay, now I need more pods, and Kubernetes will create more pods. And the deployment / replica set is useful for a stateless application. So like I said, the web application could be considered stateless, whereas a database server might be stateful. And so you would put the web application in a deployment. And so when you say, okay, I want X number of nodes in my deployment, then Kubernetes will basically create those nodes everywhere that it needs to create them, and it will make sure to always have that kind of that number of nodes running. And this is actually what we call in Kubernetes, you create something called the desired state, which is basically the description of what you want, and then Kubernetes will do as much as it can to make sure that the resources that are running are what your desired state is. Okay, so I said stateful. No, the deployment is stateless. What about a database? A group of database servers would obviously be stateful, because we need to keep the data around. And so Kubernetes has something called a stateful set that does exactly that. Is a group of stateful pods. What is interesting with this, the stateful set, is that is the fact that it keeps a storage. It has options to have individual storage for each of the pods, and it keeps also a status of the ordering, how the pods, when they're started, they start in the same order. Okay, and then the last thing I want to talk about, like the basic fundamental resource provided by Kubernetes, is the service. And this is basically the network access to use the a pod or a deployment or a stateful set. So basically, a service will can create an IP address that is used to access those those other resources, and then it just provides basically the network, all the network infrastructure to provide access to those. It has also an interesting option is that Kubernetes provides the ability to make a load balance service. So if you have, let's say, a replica set with multiple web applications, you can tell Kubernetes, okay, I want to create a service, a single IP address to access any one of those web apps in a load balance manner, and then it will do load balancing for when connections come through the service. All right, so we saw the fundamentals of Kubernetes that we're going to be using with the operator. Now, because the operator, the main purpose of the operator is to run MySQL InnoDB Cluster in Kubernetes. Let's just take a quick look at what InnoDB Cluster is, in case somebody is not familiar. So MySQL InnoDB Cluster is basically multiple MySQL servers running together as a group. They are self-managed as much as possible, in the sense that they're aware of each other, the status of each other. They know how many servers are in the group. Whenever a new member joins the group, then the other members are alerted and they accept the new member. So it's kind of a they work essentially as almost as a working unit. It's a working group, and so we have in this group we have one server that is called the primary. And this is where the applications would send their writes, let's say inserts, deletes, updates, go to the primary server. And there's a push mechanism, a push kind of replication that happens where those changes are sent from the primary to the secondaries. And this is done, at the commit time. So it's a push mechanism, which is unlike the traditional replication of MySQL, which is more of a pull mechanism where the replicas request the latest changes from the source. So this one is the opposite direction, is a push. And so what is nice about this, aside from being faster and more, let's say, more immediate, is that it also provides a guarantee of no data loss, because the changes are pushed automatically on the commit time. They're part of the commit process. But then how would an application know which of the server is currently the primary? Because at any moment, the group may decide within itself, okay, which one of us is the primary? Perhaps the current primary is having a downtime, then the group elects a new primary. So how would the application know where to connect? So we have a middleware software called MySQL Router that MySQL provides. And it's a very thin layer of software that just basically knows which one is the primary, which one is the secondary, and then it sends the connections to the primary. Okay, it sends the right connections, especially to the primary. And then to manage the InnoDB cluster, we use a tool called MySQL Shell. So if you're on premise, you have, let's say, 3 MySQL servers running, you can group them together to be an InnoDB cluster. You would use the MySQL Shell to do that. Okay, so then what happens if, the main purpose of this is high availability. So what happens if the primary is not available? So the rest of the group detects that automatically. And it only takes a few seconds for the group to settle on the fact that the primary is gone, and it's time to elect a new primary. And so the failover happens automated within the group, and they elect that there's a new primary. As this happens, the group notifies in real time the MySQL router that there's a change and there's a new primary. And so the MySQL router points immediately to the new primary. And then the application can reconnect and will go directly to the new primary. So there's no change at all here that is involved at the application level, because you just connect always to the MySQL router. Yeah, so everything that I spoke about just now is fully automated by the MySQL InnoDB cluster. That's kind of the main purpose of running InnoDB clusters to automate the failover and hide all the complexity, both from the application and from the person that manages the the MySQL environment. And then when we bring back the primary, or if we have, let's say, a InnoDB cluster that's running and we just add a new member to the primary to make the group bigger, then what happens is that we use the MySQL shell to bring it back. Or if it's an existing server that just restarts, it rejoins automatically. So when the server joins the group, it has, and again, this is automated as much as possible. So the new member basically clones itself from the rest of the group. So there is a cloning mechanism in MySQL where a server can basically download all of the data from another server. It fully synchronizes to be at the exact moment of the rest of the group, and then after that it becomes online. So until a server is fully synchronized, is running, but it's running in an offline mode that it doesn't accept connections, and then when it is fully synchronized, that's when it becomes a full member again of the group. So this is automated. And with Kubernetes, this is even better because the full thing is like basically the application doesn't even know about any of this. Actually, this is how it would look in Kubernetes. So if we go back to what I was talking earlier, the deployments, the services, the Kubernetes objects, and if we apply those to InnoDB cluster, this is how it's going to look like. So we see the pods. The pods are basically the orange boxes, the yellow-orange boxes that contain the MySQL software. So we have the MySQL router, we have the MySQL servers in the middle, and then we have the gray kind of boxes that are the deployments and stateful sets. So we see that there's a stateful set that contains the 3 MySQL servers, and this is in the center of the screen to the bottom. And these are working together as as a group. And then above that, there's a replica set or deployment of MySQL routers. And the nice thing is that the service that provides network access to this entire thing, especially to the MySQL routers, is configured on the screen. The word LB is load balancer. So we can configure the service to be a load balancing service. And so when connections come to the MySQL routers, the Kubernetes service does a load balance to router number 1, router number 2. If router number 1 is not, or I should say 0 and 1, you could grow that very easily to any number of routers. If the current router that an application is connected to is not available, then Kubernetes itself will move or will basically route the new connections to the remaining MySQL routers. So it's a very pretty implementation of high availability for the MySQL routers. And at the bottom of that, the MySQL servers themselves, they provide their own high availability by using both Kubernetes and by using the group replication mechanism that is there to do the failover and the primary election. Yeah, so this is kind of what we're going to do with the operator. We're going to have something that's like on the screen right now. And just one final kind of topic before we jump right into the operator is how storage works in Kubernetes, but especially in the context of database servers, with MySQL. So, of course, the purpose is to keep data, is to store data when we use MySQL. So we're going to create storage claims, volume claims that are going to basically store data outside of the Kubernetes pod into another storage unit. So if you're in a cloud, for example, it could be block storage, or it could be just hard disks, if you're on premise. And so what we do when we create the pod is that we configure the MySQL containers to have persisted volume claims. And typically you would have one, at minimum one, for the data dir. In the MySQL data dir is where we store the database. And then you could have other ones, let's say for the backup, if you do, MySQL has, let's say, extensive auditing capabilities. So you could have another storage volume or a persistent volume claim to keep audit files. So yeah, and this is available when we use a stateful set. That's kind of the difference between a stateful set and a replica set / deployment, is that the stateful set has a persistent volume claim, or has persistent volume claims that are individualized for each of the pod that are running in the stateful set. And this is kind of like as mentioned, the desired states is the kind of description of what you want. So if you're going to create a stateful set for let's say 3 MySQL servers to run as a group, then it's very simple in Kubernetes. You make the description, which is the YAML file. You say, okay, I want a stateful set of 3 replicas, and then you say which image, Docker image to use, or I should say container image to use to create those those containers. So it's really that simple. And then at the bottom, you can declare the persistent volume claims, where to store the data. For the routers, basically the same thing. You just have, in this case, you could make a stateful set or a replica set or a deployment, and you use the image for the MySQL router. All right. Now we're well equipped for the next, for the main part of the presentation, the meat of the presentation, which is the MySQL operator for Kubernetes. So everything I talked about, you can do manually, works perfectly well, no problem at all. But how about we make it even better by providing the official way that Kubernetes has with operators to do this in an even easier way. So the operator that MySQL has developed for Kubernetes provides basically the full life cycle for the MySQL InnoDB cluster running in Kubernetes, meaning that you use the operator to create the InnoDB cluster. You use it to perform tasks like rolling upgrades to go from version X to version Y of MySQL. You can do also grow the server, the cluster size. If you have 3 nodes and you want 5 nodes, then it's really simple with the operator. And so yeah, this is the goal for the operator that we have for when we decided to make the operators to be able to do a full life cycle, to provide full life cycle for the MySQL InnoDB cluster running in Kubernetes. And we used as much of the technology that we created in MySQL to make this possible. For example, I mentioned earlier that MySQL has the ability to clone itself from another MySQL server. So we make use of that in Kubernetes to make it as quick and seamless as possible when we grow the size of a cluster. Another thing is we support MySQL. We have the community edition of MySQL. We also have the enterprise edition of MySQL. So we just make sure that the products that we provide are supported. So some of the specific goals that we have with InnoDB cluster running in Kubernetes. So first off, as I mentioned, because MySQL InnoDB cluster uses a push kind of replication between all the nodes, then we are able to have very strong durability, that as soon as a commit happens, then you know that the data is not just on that server, but is also on other servers. So if you lose at a very inconvenient time the primary server, then it's okay. It's okay in the sense that the data is not lost. Okay, the last transaction really is available elsewhere because it was pushed at the time of the commit. If you run InnoDB cluster and a Kubernetes cluster, most likely it's going to be on multiple computers. Obviously, the way to run InnoDB cluster, the best way is to run each node on a different physical node. to make sure that each pod in a different physical environment, just to make sure if you lose the physical environment, you don't lose everything. But it does bring up the possibility of having a split brain, meaning that if you have, let's say, 5 MySQL servers, and all of a sudden there's a network glitch where 2 are isolated from the other 3, then InnoDB Cluster knows that this is happening, that they can only reach, let's say, 2 servers. So then these servers go into read-only mode, or you could have them to shut down themselves entirely and become unavailable. So we protect against that possibility, and this helps to have in terms of durability, because you cannot write new data in a minority environment. Okay, it's always it goes to the majority of the MySQL servers. There won't be any conflicts. In terms of read scaling, also that's an objective, of course, of InnoDB clusters, that if you have 3 servers, yeah, sure, it's for high availability is the main purpose, but why not make use of the other servers for for scaling the reads as well, since the data is available on them. And what we want with the operator is to be able to create or scale, let's say, new servers up, but at the same time we could also scale down. If you may have a time of the day where you have more there's more demand on the InnoDB cluster. You want to scale up the size, so you can do that with the operator. And then when you know that it's time to scale down, then you can also do that with the operator. It goes both directions. And of course, high availability, that's the main purpose of it, and hide the fact there's a failover from the application and from the end user. So when we create a cluster in InnoDB cluster in Kubernetes with the operator, this is what we get. It's basically what I showed earlier, but from a slightly different angle, in the sense that we see there's a replica set with pods for the MySQL router. There's a stateful set with pods for the MySQL servers. And if you remember, I mentioned earlier, we have, Kubernetes has the concept of a sidecar container in the pod that you could use to basically do health checks of the main container. So the MySQL operator comes built in, it comes with an agent that whenever it creates MySQL servers, it puts the agent within the pod as a sidecar container. And then this agent is used to do some of the InnoDB cluster management. For example, it configures the MySQL server to be used for InnoDB cluster. It helps when it rejoins the group, things like that. So the MySQL operator bundles that sidecar agent with the MySQL server. From an end user, this is completely hidden. You do nothing. You just create the cluster, and with like one command line, and what is on the screen is what happens in Kubernetes. And also we see how the operator also creates the persisted volume claims for the stateful sets. Of course, you edit, when you create the cluster, you specify these details where to store the data. The container images that we use with operator, the official ones by us, by MySQL. So there's basically 2 main containers, container images. There's the MySQL server, obviously, and there's also the MySQL router. The community edition version of MySQL of these containers are available on a Docker Hub. You can just do a Docker pull and get those. And also we have MySQL has the community edition, which is the open source free to use version of MySQL. But there's also the enterprise edition version of MySQL that contains additional security and privacy functionality. It includes also a backup tool for let's say live backup and so on. So this is also available as a bundle, and to download those container images, you can get them from the official Oracle container registry, which is the link is on the screen. as well as it can be downloaded from edelivery.oracle.com, where the latest Oracle software is available, as well as if someone has a support contract with Oracle, support.oracle.com is where you get that. And when I say support contract, in the case of MySQL, it is a MySQL enterprise subscription. If you have that, you can download it from the support website of Oracle. And by the way, this is MySQL 8. Okay, so it's not MySQL 5.7 or MySQL 6, 5.6. This is MySQL 8. This is where we a lot of the new functionality to make it really nice in Kubernetes, like the cloning, is part of MySQL 8. So we need MySQL 8. Okay. There are some popular Kubernetes environments that we see with MySQL, especially. There's a K3S, which is by Rancher, is a lightweight Kubernetes environment that is pretty easy to use. It's pretty much all inclusive, so you don't need to worry too much about the going deep into the weeds of how to set up Kubernetes. There's also MiniKube, and this is so it's an even lighter weight version of of Kubernetes, in the sense that it runs on your local computer. It could be your laptop. If you're doing demonstration, then most likely MiniKube is the way to go for Kubernetes. And it runs locally. It uses either virtual machines or even Docker containers to run the pods. So you can make your, if you want to demonstrate or test MySQL InnoDB cluster, you could just use MiniKube on your local computer, and it's gonna create 3 local, pods running InnoDB cluster. And there's as well, another famous, at least, with Oracle, we have the Oracle Container Engine for Kubernetes, and that is a fully managed service, Kubernetes service that is in Oracle Cloud, that you can basically upload the MySQL images and create your DB cluster there. So because all of these are Kubernetes, what is very nice is that all the commands to run InnoDB cluster and the operator, they're all the same everywhere. So even though it's like 3 different flavors, it's the same. It's the same way we use them. We use them the same way, pretty much. Okay, so I mentioned the Oracle Cloud or the Oracle Container Engine for Kubernetes. And the reason I want to bring it up is that when you create MySQL servers in Kubernetes, of course, most likely it's because the application itself is going to be running there. And so the way that Oracle Container Engine for Kubernetes works is we have the Kubernetes itself, the Kubernetes service, but there's also a registry for the cloud, for the container images. So the two kind of go together. And so, yeah, so you run the pods and the services in the container engine, and then you can upload the container images in the registry, and then the container image can pull from the registry, or the container engine pulls from the registry. And then the nice thing running in the cloud environment is that you have the ability as well to integrate with the other types of the other services that are available in the cloud. So somebody who creates what we would call a cloud native application that makes use as much as possible of the cloud services and the benefits, like, for example, the scaling, the unlimited storage and things like that. So you can run MySQL in that environment in the Kubernetes engine in the Oracle Cloud. And then the application can also make use of, for example, the monitoring, notifications, the streaming, and all the other services. And cloud native is not just some, let's say, marketing gimmick, but in fact, a lot of new applications, especially in the clouds, they're designed as much as possible to make use of the various cloud services, like the ones I mentioned, like unlimited storage and so on. So it's a big direction. So for us, for MySQL, it's important to be there, because we know that there's let's say a big movement in the marketplace, going towards cloud and kind of cloud native applications. So we want MySQL to be a player. So we make this operator to be, to make MySQL as nice as possible in running in Kubernetes. But also, it's not just running MySQL in Kubernetes, but as well in the case of Oracle Container Engine for Kubernetes, it is possible for the applications that run in the container engine to make use of the MySQL database service, which is the fully managed service. So we have both ways. You could use the MySQL operator to run MySQL within the container engine for Kubernetes, or the applications that are running there could access the fully managed MySQL database service that is provided, as part of the Oracle Cloud. And for that, you can create endpoints to do that. And just in general, also, like the Oracle Cloud has service brokers that do a mapping of the cloud services to basically endpoints. It makes basically services in Oracle in the Kubernetes engine to refer to services running outside in the Oracle Cloud. So that's the service brokers. So anyway, just to point out that as much as I'm pushing, I want to make the MySQL operator be a good thing to use. That is great, but you can also use the MySQL database service externally to the Kubernetes engine with the same applications. Okay, so let's get back to the operator. So in the case of Kubernetes, you create the repository, which is what I mentioned, and then you can upload the container images, whether community or enterprise. The applications also, you upload them to the repository, and then create a tag in the repository, and then after that, the operator is going to be able to use the image definition or the image specification that was tagged in the registry. And by the way, in the like I said, the repository in the Oracle Cloud for the container images uses object storage, and the OCI compute nodes are basically the foundation for the pods. The pods are going to be running. If you create a 10 node Kubernetes cluster in Oracle container engine, it's going to create compute nodes, and then the pods are going to be running there. All right, so how do we install the MySQL operator for Kubernetes? Very simple. So first off, it's available from GitHub. So just go to GitHub, and you can download the YAML file from there, or you can just even point. You could just apply, the YAML files directly from the web. And so you have to apply two YAML files. First is for the custom resource definition, and then secondly, and that's going to create, all the definitions for the operator, and then we deploy the operator itself with just by applying the YAML file called deploy operator.yaml. So at that moment, when you do that, you got the operator running, and the operator, by the way, runs in Kubernetes as a pod. So what you could do is find out, okay, what is the operator name, and you can look at the pod information. So you can do get pod and look for the the namespace MySQL operator, and then you will see the operator there. It's going to be MySQL operator and then XYZ, and you can describe it once you have the name. So now we want to create a InnoDB cluster. How do we do that once the operator is running? So first off, we need to create the root account, like the information for the root account. So that's going to be the username, the host name, and the password. And we use the Kubernetes secret to do that. So you just create a secret. In this case, I'm calling it my passwords. And then once we have that, you can use you can use a YAML file that's gonna make use of the operator to create the InnoDB cluster. So there's going to be an object of the kind InnoDB cluster that is basically the MySQL operator. Like it's basically done by the MySQL operator. And so you create your MySQL cluster. In this case, I name it my cluster, and you can see it on the box on the right of the screen. I give the root account information, but with the secret name, my passwords. I define my cluster to be 3 MySQL servers and 2 MySQL routers. And then what is going to happen as soon as I press apply, Kubernetes will create 3 pods. It's going to create basically a stateful set called my cluster with 3 pods running. And the pods are going to have the agent and the MySQL servers. And also it's going to create the persisted volume claim to store the data there. And as part of when you create the YAML file, like on the right side, there's some fields to have the data there. You can see where to store the data there, and some of the other information. And so it's going to create the stateful set. It's also going to create a replica set called MySQL -router. Then this is obviously for the MySQL routers, and it's going to make the appropriate services, but it's going to create one service especially called my cluster in this case, and this is what you use to connect to access the MySQL InnoDB cluster. So you see, it's very simple. You just make this very simple YAML file, you apply it, and bam, now you got your InnoDB cluster. If you want to take a look at it, to watch it, you can watch it very easily. You just get you just basically get the pod and you watch it. You can get the service, which is going to give you the IP address to use. Just do a kubectl get service and my cluster, like basically the cluster name you gave. Same with the PVCs. Once you have the pod, the pod is going to be MySQL. It's going to be my cluster -0, 1, 2, and you can look at the data there. The name of the PVC is data there my cluster -0. So it just basically put data there in front as a prefix. And you can also take a look at the services, and you can even, if you want to have applications that exist outside of Kubernetes, access that MySQL InnoDB cluster, you can do a port forward of the service, or you can define it to do a load balancing as well. So yeah, it's very, very simple, just these very simple commands, and you have your MySQL InnoDB cluster running. Now, speaking of simple commands, let's go to another one. How about we scale the cluster from 3 nodes to 5 nodes? And at the same time, let's add a router, a MySQL router to that. Very easy. There are 2 ways. You could just basically edit your the YAML file, that defines the cluster, and then just apply it, and then Kubernetes will make it happen. Or you can edit, kubectl edit, the my cluster, and then you can just edit the values. So in this case, all I'm doing to go from 3 nodes to 5 nodes is I change the number 3 to 5, and when I apply it, when it's applied, then Kubernetes with the operator just take care of everything to bring it from 3 nodes to 5 nodes. So this is a no downtime operation. It's 100% automated. All you have to do is watch it, watch it happen live, and it will be done. Now, I just want to give a caution, is that I mentioned earlier that when we create the cluster, it creates a stateful set, it creates a replica set. These are kind of the underlying objects of the cluster. Technically, you could take a backdoor and go to those objects, and scale the stateful set directly, or the replica set directly. You can do that. The only problem is that it won't be reflected in the Kubernetes will do it. You will have, let's say, 5 nodes if you do that. But if you look at the InnoDB cluster, the definition itself of the InnoDB cluster object won't reflect that. So the best way is to edit the InnoDB cluster object and then it will get pushed down to the stateful set and the replicate set. It doesn't get pushed up. And the same mechanism as scaling, you do it the same way for upgrading the version of MySQL. So let's say now the latest version at the date of this webinar is 8.0.25. 8.0.26 is due out anytime. So how would you upgrade from 25 to 26? Very simple. You just edit again the definition of the InnoDB cluster. There are fields that indicate the version. You change the version to the version that you want, and then apply, and that's it. The Kubernetes will manage it, will take care of it using the operator to upgrade in a rolling upgrade manner. So basically no downtime, your environment. So the way it does it, kind of like in the details, is that you have your, let's say you have five pods of MySQL servers running. So it will go from pod number 4, shut it down, do the upgrade, then 3, 2, 1, 0. So yeah, so it goes from like the last one to the first one. And this is again a rolling upgrade. So you always have a primary that's available. Just a kind of a tip. It's not even necessary to do that, but it's a tip to make your this even better. Is that it might be better if you make the if you make sure that the primary node is on the pod 0, the first pod, just because then in that case you don't get as many failovers. You just get one failover at the very end of your rolling upgrade. So one of the goals also with the operator is to improve the self-healing aspect of MySQL InnoDB cluster in Kubernetes, and frankly the Kubernetes environment, the Kubernetes system in general, at large, provides excellent functionality for that, in the sense that if the pod has a problem, or excuse me, if the container within the pod has a problem, then the container runtime itself will try to restart it. And then if there's an issue with the pod, then Kubernetes will try to fix it. If the host is not working, then Kubernetes will try to make sure that it's running maybe on another host. So Kubernetes does a lot of the work, but to make it make it seamless and 100% automated in the context of InnoDB cluster, then that's where the sidecar agent that we bundle in the server pod comes in. Is that it just ensures that the MySQL server rejoins the InnoDB cluster and in a very healthy manner, and also synchronizes, and is basically so as the person that manages that, you don't need to do any of that. The sidecar agent helps to automate all this, helps Kubernetes to automate what's happening. There's also hopefully something that never happens, but if it does happen, if the entire cluster, maybe the Kubernetes cluster itself, is shut down in some way, and there's no MySQL servers running at all, then the MySQL operator is able to restart the complete cluster from not running at all to a running cluster, if there was a complete shutdown. And a final thing, that I want to bring up to you, to introduce to you, that we can do with the operator is, I was talking about creating the operator, managing it, and all that. But what about, the full life cycle includes the sad moment, the ending of it. So you can delete a cluster very simply. You just do kubectl delete. And the operator will take care of deleting all of the resources, that the pods and the stateful set, the services, everything that is built, that was part of the cluster, gets deleted by the operator. Of course, the persisted volume claim, you don't, the data itself is not deleted. Okay, so you're good there. So this concludes pretty much, what the introduction to the Kubernetes operator. It is currently in a beta release. You can find it on GitHub. Just search MySQL, on the MySQL operator, and you will see it's released by the Oracle team, the MySQL team at Oracle. There are a variety of MySQL operators out there, including some previous ones by Oracle. The one by the official one by us is really a github.com/MySQL/MySQL operator. The GA release will be forthcoming. I don't have a date, unfortunately, to provide, but it is, the beta is before the GA, so it should be pretty soon. And please, if anybody wants try our operator, if there's any feedback to provide, come to our forums or post issues on GitHub, and our team is, will be right on top of that. So I think that the goals that we set for ourselves to basically provide a much better way to operate MySQL InnoDB cluster in Kubernetes, make it even more reliable and high availability with automatic rejoinings of the nodes and all that, and just basically offer a more seamless way of doing MySQL in Kubernetes, in a way that's more native to Kubernetes. So I think that the MySQL operator does meet those goals that we set out, and over time, of course, we will expand the functionality to be responsive to what people need. Just in conclusion, I talked about the Oracle Kubernetes engine that we have, Oracle Container Engine for Kubernetes, the MySQL database service, and all these things. So just to raise the awareness that we do have a free trial. If you want to try those services, you can just sign up and get the free trial and run your Kubernetes services in Oracle Cloud, MySQL services in Oracle Cloud, and see if it works for you. To talk with us, there's of course the mysql.com, which is our website for MySQL. There are forums if you have any questions, but also please follow our Twitter, Facebook page, and keep in touch with us. And like I said, also if you have any problems with the operator, you can raise issues on GitHub. And final thing, just on a general note with MySQL, if we are very open to anybody that uses MySQL. If you have any questions, if you want the MySQL team to take a look at your environment and provide some some advice, as well. If you have we have an option for MySQL. Let's say that you have a MySQL server or an application that runs in MySQL with MySQL, and you want to have a much higher performance. We do have options to do that, so we can help to explore those options. So the option is called the Heatwave. So if you want to check what is available for you, just reach out to us, and we'll be happy to get in touch. Thank you for attending our introduction to the MySQL operator for Kubernetes. I hope that I hope people try it. I hope you try it. And if you have any feedback, again, please do give it to us, and we'll be happy to receive it and act on it.